Hello students, welcome to lesson number 3 in this chapter, limits and derivatives. In today's lesson, we will learn about calculating or evaluating the limits using what are called limit laws. Okay, so first we will go through the list of the limit laws in what we call the properties of limits. In that, you will find that some are obvious or self-evident. Some require a little bit of explanation. One particular law, if I remember correctly, and maybe some properties are again something that I would request you to keep in mind very importantly when it comes to solving the problems later on. Okay, some will be so obvious that I will not ask you to remember them. There is no way to think otherwise in those laws, but some laws students often tend to overlook. They're so simple that people overlook. Okay, so I will talk about that. And in that, one of the concept will be the direct substitution. We'll discuss that. And then we will talk about limits when the two sides at a point are different. Okay, on the left and the right, the functions are the rules are different. Sorry, not the function. The function is the same. The rules are different. Then how do you look at the limit? And then finally, we will discuss the very important theorem called squeeze theorem, which is used in proving some limits when the function is difficult to handle. Okay, in a particular way. Again, we will discuss that when we reach there. Let me start. So first, we start with properties of limits. And let me see, you should be able to see the full screen. Yes. So here are some well-known limit laws. Okay. And in all of these properties, make note of them. Please write them down. Okay. Just seeing them is not going to help you. Once you write down, you don't have to write many times. Once you write down, it helps you remember them and apply them. Okay. So in the limit laws, C is a constant, and suppose there are these two functions f and g whose limits at this point A exists. So there are some assumptions here. Okay. For example, if one of the limits does not exist, like either f of x or g of x, does not have a limit at A, that's none of these laws make sense. Okay. Then, any of these expressions, the limit will not exist. Right. So we start with the assumption that both individual functions have the limits at that point at a finite value. When I say limit exists, it's a finite value, and there is a constant number c. Okay. Then the first law simply says that the sum function, right, the function that you would obtain by adding the two functions, like let's say x plus sine x, the limit of that function x plus sine x would be the limit of x and the limit of sine x at the same point added. So in words, some many of these properties are described very nicely in a sentence. We say that the limit of the sum function is the sum of limits at the same point. Okay, limit of the sum of two functions is the sum of limits of those functions. Process that. Okay, same idea applies when you take the difference, when you take a constant multiple. This last property, this third property here is again very useful. Don't overlook it. Okay, many times students do overlook. Whenever there is a constant multiplied to a function, or there is a function given which has a coefficient, take it as a coefficient. If it has a coefficient, you can take the coefficient out of the limit process basically. Okay, and find the limit of the rest of it and multiply. Don't forget to multiply, with the coefficient at the end. But okay, and you can also do the same thing if it is a product. If you are multiplying two functions, you could as well multiply the limits of those functions. at the same point. Okay. Now, so far so good. The fifth property given on the right side is where you have to be careful. Why? Because we are dividing. Okay. When you divide, everything is good if the denominator is not 0, right? So that quotient function has a limit given by the quotient of the limits of the functions provided the limit of the denominator is not 0. Okay. What else? These 5 laws can be stated verbally like that. Okay. The sum law, we call them sometimes, if you have to justify or give a reason, oftentimes we ask you to give a reason for your work, right? So you can just mention sum law, difference law, constant multiple law, right? The first through. The name should be make it clear, okay, what that law is. Product law, quotient law. Okay, those 5 laws, right? First set up some basic properties. Here is going to be some examples with the help of a graph. It will be more clear. Okay. We will do that. We will solve them and then we will check the answers in the slides here. Okay. Evaluate. I'm zooming in to show you the question clearly. Evaluate the limit of fx plus 5 times gx as x approaches -2. Okay. So let's go to the graph. Um, it looks to me and the -1 should be here and -2 should be here, right? So at that point, a limit of f, the purple one is f. Okay, limit of f is 1 and the limit of g is -1. Okay, the value of the function is different and you remember that concept, right? The value of the function can be different from the limit. The limit is here. Limit of f is 1, limit of g is -1 at -2. Okay, and that means according to this law, what will happen? 1 plus 5 times -1, as simple as that. But if you are showing a detailed work, you will break it down into 2 steps, right? First, use the sum law to separate f of x plus limit of 5 times g of x, and then you can extract the 5 out of the limit by using the constant multiple law, and the end result will be this, okay, which will be -4. Limit of f of x times g of x as x approaches 1. Okay, let us look at the graph again. F of x times g of x as x approaches 1. 1 is here and the value of, okay. Now the limit of g of x does not exist at this point, right? The left-hand limit and the right-hand limit of the function g of x are different there. Good opportunity to review that, what we studied earlier. Okay, I'm going to write here limit x approaches 1 from the left. We say 1 minus for shorthand, limit as x approaches 1 from the left of the function g of x is, you write your answer and check with me, -2. Okay, limit as x approaches 1 of the function g of x from the right is -1. Okay, hence the limit of g of x as x approaches 1 does not exist. So once that limit doesn't exist, this whole thing does not exist. All right. And if you look at the right side, limit as x approaches 2 of the function f of x over g of x. Okay, where is 2? 2 is here. And the problem there you can immediately see, limit as x approaches 2 of the function g of x is 0, right? It's exactly intersecting the x-axis at that point. Hence, this limit also does not exist. Okay? You don't have to worry about f of x, If the denominator is 0, it does not exist. Let us check our answers. That seems good. And over here, what do you see? Yeah, so our conclusion was fine. So this does not exist because those two limits are different. Okay. Looks like the values are read wrong. Was the scale different? It says -2 and -4, but where did they get that from? It's not clear to me. Oh, f of x times g of x. Okay, if you multiply that, that would be the case. Okay, all right. And here that is 0, so the limit. The numerator is a non-zero number, but the denominator is 0. Okay, which reminds me, see, I earlier made a statement that, don't worry about f of x. Now I should say, no, that was a mistake. Okay, I correct myself. You have to care for f of x because it has to be non-zero for you to confidently say that the limit does not exist. Okay, because non-zero divided by 0 is either plus infinity or minus infinity. Right? We say it is undefined. If both are 0, that is an indeterminate case. Okay, there is a difference between, I don't know if I said this, like elaborated on this idea before. I don't think so in this lecture series. So this is something very important you might want to pay attention. Okay. When it is 0, 1 divided by 0 is usually either plus infinity or minus infinity. Okay. So that is, we say it is undefined, but there is some idea, it's either very large positive or very large negative. But 0 divided by 0 is indeterminate. That is a different category. So it's not large, it's not small, it's not positive, it's not negative. We don't know anything about it. That's indeterminate. Okay. And usually what happens is, in such cases, not usually, sometimes what can happen is you rewrite the function, cancel some factors, sometimes you can factorize polynomials, right? Get rid of some factors or do some rationalization, do some, later you will study a law called L'Hopital's law, use some techniques, and then it is no longer 0 divided by 0. You modify and then apply the limit and you are suddenly able to find a value for that function. Okay. So this, if it is 0 divided by 0, it can go either way. Okay, exists or does not exist. Okay, and so I was saying it is important here that numerator is non-zero and denominator is 0. Hence you can say limit does not exist. It's going to be asymptotic, plus or minus infinity. Okay. Moving on here, two other, like I was saying, some very simple and important laws that I have seen students overlook, so I'll talk about that here. The power law, the root law, all of this. Okay, what that basically says is, if the limit of a function exists at a point and you have to evaluate the limit of a power of that, okay, exponent of that, you don't need to do anything differently. Just take the limit of that function and raise it to the same power. Okay, and if you, those of you who are proof inclined, you want to think like, how does this or why is this the case? That actually comes from repeated application of the product law, right? Think of f of x whole squared at first. That is f of x times f of x. Now you can use the product law to say that it will be limit of f of x times limit of f of x as x approaches a. Okay, that means you are whole squaring the whole limit and repeat that. And by induction, you can prove that this will be the case. Similarly, okay, not from induction, the next one, the root law might require some a little bit more in its proof, but you get the idea. Okay, you could do the same thing if you are taking the square root. And but here you have to be careful. If you are taking an even root, you need to make sure you are taking an even root of a positive or at least non-negative number. It should have said equal or greater than 0. Correct that there. Okay, you can do that for equal or greater than 0 if it is non-negative. I, I mean, if n is an even root, like square root. If you are taking cube root, no problem. Okay. In finally, these two are again very super important. Okay. If you just have a constant, there is no x, then it doesn't matter where you take the limit. Its value is the same, constant. Okay, that's like your constant function. If you think about it, you have your x-axis and y-axis, and you have a constant function. Now, at any point, it has the same value, right? So limit of a constant function is the same constant. And the next one is the limit of the function y equal to x. Okay, if you take this line y equals to x, at any point a, its limit is that a, right? Okay, you can just substitute a for x. And the number 9 here, we will see in the next slide or two, is not only for x, any polynomial. Okay, as long as it is defined, you could just substitute. So most of the time limit will be boring. Okay, I will say that. Most of the time the limit of a function is boring because it is going to be just the value of the function. You evaluate the value of the function. When it is continuous, the concept later we will talk about. So limit is most of the time boring because most of the time the function will be continuous. Limit only becomes interesting, okay, when two sides have different values or it goes to infinity or there's a hole in the graph, that's when limit is different from the value of the function, it is interesting. Okay, so what you are seeing in number 9 is the boring step which you can do most of the time in most of the functions. Just substitute. Next, we will combine the properties that we just talked about to combine some of them to produce more powerful results. Okay, so if I can find the limit of this identity function by simply substituting the value of x, and there is previously the power law which says that the limit of the power of a function is the power of the limit of the function, right? If I combine them together, I get this. So the limit of x to the n is equal to a to the n. Now think of combining this with the constant multiple law and the sum law and the difference law, and you could see that the limit of any polynomial will be the value of the polynomial, and not just polynomial, the idea can be extended to other functions which have that property called continuity as long as they are continuous. Okay, more on that on the next slide where we talk about direct substitution. On this page, we end with the idea that this can also be extended to roots as long as you make sure that the value under the root is defined, which means if you are odd root, no problem. If it is an even root, make sure the quantity under the root is non-negative. Okay, so that evaluating limits by direct substitution. By using all the properties that we just mentioned and synthesizing them, we come up with this idea. What does it say? If f is a polynomial or a rational function and the value at which you are evaluating the limit is in the domain of that function. Remember that automatically means that you are not going to take a value where the denominator is 0 in the rational function. The values where the denominator is 0 are not in the domain of the rational function. Okay, so if it is in the domain, that means the denominator is not 0. If the denominator is not 0, you can simply substitute a for x and evaluate the function, and that is your limit. In fact, I would go one step ahead and say this idea that we are generating here is not just for polynomial or rational function. This is true for, I'll write here below, okay, all what we call elementary functions in their domains. I should add true for, okay, I should say true for all elementary functions in their domains. Not functions in their domains. That statement is true for the elementary functions as long as that A is in their domains. Okay, please understand it in that sense. What are elementary functions? Polynomial functions, rational functions. Later we will see some trigonometric functions, the root functions. Okay, the functions which what we call are continuous in that domain. There is no hole basically, or there is no jump as long as they are in the domain. Okay, you can directly substitute. So here is an example. If I were to evaluate limit as x approaches 3, the function x square minus 1 over x minus 1. Okay, the fact that this is a rational function and there is a denominator, I don't have to worry in this case, because as x approaches 3, the denominator will be 3 minus 1, which is not 0. So the limit in this case is simply substituting 3 for x. Okay, so the value of the function at 3, that will be 8 divided by 2, which is 4. Okay, now what if you want to evaluate the limit at 1? No, then you cannot do the direct substitution. And when you cannot do the direct substitution, you cannot do the quotient law either, okay, because the denominator is 0. So we have to do some algebra. What algebra will you do? Take that x square minus 1 and write it as x square minus 1 square, and then use the factoring formula for a square minus b square. A square minus b square can be factored as a plus b times a minus b. So that x square minus 1 square is factored as x minus 1 times x plus 1. In which case, you would be able to cancel the x minus 1 as a factor. When, as long as x is not equal to 1. Okay, because otherwise at 1 it is 0 divided by 0, there is a problem. And that's okay. We can cancel here, and x is not equal to 1 is okay, because limit as x approaches 1, you are only approaching 1. Remember the idea of the limit. We don't bother about what exactly happens at the value. We are only interested in values near that point. So as you are getting closer to 1, not equal to 1. So x is not equal to 1 as far as limit is concerned. So it is safe to do this cancellation. And after you do this cancellation, and you are left only with x plus 1, in which case, when you substitute now, you get the value 2. The limit is 2. Okay. So as you might remember now, this from the your pre-calculus or college algebra, the graph of that function was actually this. Okay, that function x square minus 1 over x minus 1. If you graph that, you can try now also. Take any graphing calculator and graph it. Actually, you won't even see the whole, because in theory, that is just a point where it is missing, right? So you really have to zoom in to the resolution of the level of one point, to see that whole. So you actually, when we draw it by sketch, we enlarge it and we show it like that. Okay. In theory, that's just a dot where there is a break in function, hole in the function. Okay. You will see in in fact on a calculator graph or any other graph, if you just ordinarily see, you will be seeing the graph of x plus 1. Basically, what you see here, that's what the graph of x plus 1 will look like. It will look like the graph of x plus 1. Okay. So, and that height, this value was 2 here, which is the limit. Okay. And what you observed here just now is a general statement. That is, this is very useful fact. Okay. If two functions are equal at all points except at one point, okay, like in this case, if you look at x square minus 1 and x minus 1 and the function x plus 1, this function is basically that except at 1, right? X plus 1 will be defined at 1 also because it is just a polynomial. This rational function will have a hole at that point. Other than that, the graph basically looks the same, as I was talking. So when that is the case, the limits will be the same, even at that point, because limit is all about near that point, not at the point. Okay, provided the limit exists, of course. Okay, this is the reasoning. Actually, this statement here is the reasoning behind the algebra work that we do in evaluating the limits, where we do factoring and cancel out, or where we do rationalization. All of that is valid and accepted because of this statement. Okay, moving on. One-sided limits. And as I was saying earlier, you can have piecewise functions sometimes defined where you approach to one value from the left, then on the right you are approaching. Now you might approach a different value, or sometimes you might approach the same value, right? So sometimes the limit may not exist, like this case, the limits on the left and right are different. But then we can talk about one-sided limits, right? We can say the limit on the left exists, it has this value. You can say the limit on the right exists, it has this value. Only when those two values are equal, you will say the limit exists. So here is some theory about that. Okay, what is the theorem? Limit of f of x as x approaches a is L if and only if. Okay, both ways. And zoom in and show here. This is the left hand limit, right? Is the limit L, which is also the right hand limit. Okay, so this will be we will go with this definition or this formulation of the limit most of the times when a function is piecewise, okay, which has two different rules on two sides of a point. And there's one statement at the bottom here. The limit laws also hold for one-sided limits. So all that we were doing earlier, like the power law, substitution, all of that you can do with one-sided limits also. Okay, the limit laws are not just for the overall limit. Okay, you can apply to one-sided as well. So here is an example, very simple illustration of how it works. Consider the absolute value function. Okay, now by definition, its definition is x if you are non-negative, negative x if you are negative. So when you apply the limit, you can look at the right hand limit first, in which case it will just be x and the result is now 0. And then you can look at the left hand limit, in which case it is negative x but as x approaches 0, that is also 0. And because both sides the limit is 0, the overall limit is 0. Okay. Just to illustrate, that was a very simple example to illustrate. We will do more when we are doing exercise problems later. Okay, moving on. Squeeze theorem. I talked about this at the beginning. The basic idea is this. There is a function which is very difficult to handle. I'm showing you a graph here, and we'll see this example very soon. Suppose something like this, which is fluctuating badly and difficult to know whether the limit at any point will exist or not. Difficult to evaluate. But suppose you were able to find a function like this and another function like that, and guarantee. Now this diagram doesn't look really good. A little bit adjustments will be needed, so that you're guaranteed that this red one is between these two lines at all points of time. Suppose something like that. Okay. So you would say that the blue and the pink, these two functions are squeezing the one in the middle. Okay. And because both these now have the same limit at this point where they meet or seem to meet. Okay, they don't have to meet. Suppose they have the same limit at this point, then the limit of that red function also has to be the same at that point, because it is squeezed by those two other functions. Basic idea. Okay, but very useful. And here is a formal statement. Prior to the squeeze theorem, this result, which when you apply from both sides becomes the squeeze theorem. Okay, what does it say? If a function f is always equal or less than function g, then the limit of the f of x will also be less than the limit of g, right? Except possibly at a. That exception is always allowed, right? Because again, when we say limit, we are not interested what happens exactly at a. We are only interested near a. So near a, the function f is less than function of g. Then the limit of the function also has to be the limit of less than the limit of the function g. Intuitively makes sense. Okay. Now suppose you extend that to two sides. So this g of x is now squeezed between f and h. And then suppose, on top of that, the function f and function h have the same limit L at certain point. Like the graph I was showing, the function f has this limit L, and function g h has this limit, same limit L at that point. And your function g is squeezed in between. Okay. Then the limit of that function should also be L. The illustration, of the diagram that I was saying, better diagram. Okay, of course. Check it out. It is also called sandwich theorem. Fun, right? Sandwiched between two values. Okay, let us look at an example. And you might wonder, why do we come up with such statement? It is useful when the function itself is difficult to handle. Okay, let's look at sine 1 over x. Now, if you think of the graph of sine function, if you simply look at sine x, it will be smooth graph like that, right? But if you then combine that with 1 over x, the values of 1 over x separately, I will draw here. The graph of 1 over x is this hyperbola. right? And focus particularly when you're approaching zero, like in this limit here. When you're approaching zero, okay, the values of 1 over x, you can see if you are on the positive side, 1 over x is going to plus infinity. And if you are on the negative side, 1 over x is going to negative infinity as you approach zero. And you are trying to evaluate the sign of that. And sine function is simply fluctuating between 1 and minus 1. But you try to stay between 1 and you are staying between 1 and minus 1, but the angle itself is rapidly changing. So what will be the result? The result will be you will fluctuate faster now because your 1 over x values are changing quickly. So you'll start fluctuating very, very fast, and then only when you go away, again it will slow down. In fact, in the long term, it will like go down to zero. It will not forever fluctuate. And that's because 1 over x again, as x tends to infinity, 1 over x will go to zero as x goes to plus or minus infinity, right? So later on, and sine zero will be zero. So later on, it will taper down and get asymptotic to x-axis. But close to zero, you know, maybe on some interval, it will behave like a normal sine function. And as you get close to zero, it will start rapidly fluctuating. Staying between 1 and minus 1 all the time, but fluctuating. Okay. And exactly at 0, it is not defined. 0 is not going to be in the domain of that function anyways. Okay. Because it's 1 over x. So the question is, if you were to, I'll clear this page now. Okay. If you are taking any notes from your understanding, please do it. If you just look at sine 1 over x, it's clear the limit does not exist at 0. Okay. Because as we said, it's fluctuating, and at 0, it's not defined anyways. Okay. Anyways, it's not the correct word there. Even if it is not defined, the limit could have existed, but we know it is fluctuating. But now you do something else. You multiply that with x square. Think of the effect of multiplying by x square. Okay. When x gets closer to 0, x square also will get closer to 0 faster, in fact. Okay. What will be the effect of that? The effect of that is sine 1 over x is fluctuating between 1 and minus 1, but you are damping it. You are multiplying that by x square, which is really going to 0 fast. So instead of fluctuating and staying between 1 and minus 1, it will fluctuate, but it will start decreasing because x square is making it smaller, between 0 and when you are close to 0, like when you are 0.01, 0.01 squared will be 0.001, and that will really make your values very small. Okay. And because of that, what will happen when you're close to, like, when you almost reach 0, x square will almost go to 0, and it will force you to be close to 0 as well. And that will force the limit to be 0, which was not the case if you just look at sine 1 over x. Okay. So this is a very interesting example. Now let me run through the slides here. First, note that we cannot write the limit as a product of x square and sine 1 over x because this does not exist. As I explained, it will fluctuate. So using the product rule that we saw earlier, where you could split the limit, which is not going to be helpful. So we need to do something else, and that is squeeze theorem. How will we apply the squeeze theorem? Here's the idea. Sine 1 over x, we know, is between negative 1 and 1. Whatever x you take, as long as it is defined, the values of sine will be between negative 1 and 1. Now, remember the laws of inequality. If you multiply it by any positive quantity, x square is non-negative quantity, right? It does not change the inequality. Okay, and that's what we do. It doesn't change the direction of the inequality, so we do this. And then if you see, left side is negative x square, right side is x square. Both of them go to 0 as x approaches 0. And because this quantity is in between, that will be squeezed to the same limit. And here's the idea of that graph. Okay, the green is y equal x square. The blue is negative x square. Both of them have the same limit at 0, which is 0. And the red one is the fluctuating sign x square sine 1 over x. And you can see that it is squeezed to 0, although it was difficult to prove it otherwise. Other than this, it would have been difficult to prove. Okay. All right. One last thing I will say here is, why did we choose x square? You would have got the same result for sine just x, right? That is also 0. Because if x square can squeeze it, x also will squeeze it. Okay. The only problem is, that is a little bit more work. Okay, the reason we go with x square as an initial example is because x square is positive quantity. So you could simply multiply the inequality by x square and not have to change the sign. If you multiply by x, when you are on the right side, the inequality remains the same. When you are on the left side, you have to change the direction of the inequality. You can still manage to prove the same result, but more work. I think probably you have to do one-sided limits, first, and that both sides have the same limit, and then say that um, because two-sided, both sides, left side limit and right side limit are equal, the limit is 0. Fun exercise if you want to really review the other concepts also we have discussed here, but just for squeeze theorem, that's more work for the first example. Okay, hence we go with x square. Okay, and this is formally making the statement. Thank you for watching. Next video we will solve problems on all of these topics. See you there.